and not other photons. Yes?
When you say emitting photons, you mean like bouncing back photons?
Emitting means to give off. So if you excite a material, give it energy, so when we did and put the glasses on, you saw an emission line spectra, okay? What we were doing is giving the atom energy. Specifically, we were giving the electrons. The electrons on those atoms were giving off, we're giving them energy, and as a result, those electrons were then emitting photons out towards us.
They're just like creating them?
No, they weren't creating them, they were giving them off. Now, when they do that, the electron loses energy. So the electron was in a heightened state, an excited state, because we've given them energy, and so when it gives off those photons, they go to a lower energy state. Yep.
Why would the photons have like different frequencies?
Well, because Planck and Einstein had shown already that the photons don't have frequencies. Okay, the photons have frequency. The wave has a frequency. Frequency is a wave property. EMR apparently can behave if it's particle-like, and at other times it can behave as if it's a wave. And when it's behaving as a wave, it has a certain frequency. Now, it just so happens that when it's behaving as a particle, okay, photon, the energy of that particle, the energy of that photon, is directly proportional to the frequency of the wave of that particular type of EMR when it's behaving as a wave.
Okay, so if like in the problems we did where we like drew the photon, that wave would have like one frequency, right? Like one color of light would have one frequency.
Right. A yellow photon would have associated with it a particular frequency. So if I have yellow photons coming down with 50 units of energy, okay, they're coming down. When it's behaving as a wave, it would have a particular frequency associated with it.
So if Einstein's explaining line spectra by saying each photon has associated with a specific frequency, like that corresponds to a particular line in the line spectra, why would like the photons from the same wave have different frequency, like correspond to?
The photons and the waves don't happen at the same time. The light either manifests itself as a wave, it's behaving as a wave, or it behaves as a stream of photons. It can't behave both at the same time. Kyle's a nice young man. You can imagine him helping an elderly woman across a busy intersection. But maybe he has a darker side. Maybe he likes to take sticks and whack little 4-year-olds on the back of the head. Okay? I hope that's not true. But I mean, even if it were, I think you would agree that the likelihood that we're going to see him helping the elderly woman across a busy intersection while whacking the 4-year-old, you're just not going to see those two dual natures manifest themselves at the same time. Okay? So Einstein is claiming that EMR has this dual nature. It can behave as if it were waves, and it can behave as if it was a stream of particles. And in some settings, it's clearly the wave behavior that's manifesting itself. And if you try to think about it as particles, you're going to have a hard time rationalizing it. Refraction, rainbows, prisms, that's wave behavior. You have to think of the light as behaving as a wave. Now, since Einstein's time in his work here, Feynman and other scientists have developed quantum electrodynamics. And so we now know it's always photons, it's never waves. And we can actually rationalize and explain refraction with particles, with photons. The math and the theory behind it is mind-blowingly intense. Okay? So we will still often talk about refraction in terms of the bending of waves as they pass through, because it's just easy to do. It's easy to understand, and it's useful. And you don't have to have advanced degrees to be able to reconcile.
So can you like explain the last sentence of that then?
Yeah, all we're saying is that Einstein is saying, look, you said a substance absorbs light. I'm letting you know specifically what's absorbing. Well, it's the electron. And how's the electron absorbing or giving off that energy? Is the electrons absorbing or emitting it in the form of a photon? Okay? It's not doing it in a wave. It's absorbing it in the form of a photon. Now, it just so happens that the energy of that particular photon that's being emitted or absorbed by the electron has associated with it a particular frequency when the EMR, when that same EMR is behaving as a wave. And when we talk about line spectra, we often talk about the frequencies of the individual lines, okay, or the wavelengths of the individual lines in line spectra, and that frequency corresponds to one of those lines. Does that make sense? Clear it up? Yep.
You said he could not explain why.
But yeah, he can't explain why the electrons are absorbing these photons and not the other photons, or absorbing or emitting these photons and not other photons. He didn't really explain that. So he did not give us a full explanation of line spectra. I don't know about you, but I'm not going to be happy until I know, well, why these photons and not the other photons. Okay? When we have someone who can finally answer that for me, then I'm going to be good. Okay? But I have a much better idea now of what a line spectra involves, what the mechanism is involved. And it has to do with the electron absorbing and emitting these photons. So it gave us a better picture of what's going on. Carrie, good? Questions? Okie doke, in that case, number 12, why was classical physics stumped by the photoelectric effect? How come? Eric?
They were stumped by this because light of light of frequency should carry increasing energy as the intensity of the light increases to help electrons accumulate enough energy to break free from the pull of the nucleus. So like a bright green light should have more total energy
It does.
than a dim yellow light, but it doesn't. But even a dim yellow light would allow electrons to break free from a metal that has a.
You're confusing a bunch of people is what Chethan is about to try to tell you. Yeah, you used green and then you went to a lower frequency yellow saying that, yeah, you see how that's sort of like starts to confuse a bunch of people. Okay, but he hit the main point, which is light of, classical physicists were stumped because light of any frequency should be able to provide the energy the electron needs to escape the pull of the nucleus. Light of any frequency, so long as you make it bright enough. Okay, you should be able to provide the energy the electron needs to escape the pull of the nucleus using any frequency. You just have to compensate for the lower frequency ones by making it brighter. Does that make sense, guys? Joe? Does it make sense?
Yeah.
Okay. And that doesn't happen. That's why they were stumped. I mean, it should work, but that doesn't work. Questions? Okie doke, in that case, number 14, or rather 13, how did Einstein explain the photoelectric effect? So how did he explain it? Kyle?
He said that as you increase the intensity of the light, the total energy increased, but that didn't affect the energy of individual photons, it just increased the number of them.
Okay. And since the electron can only absorb one photon at a time, and if it does, it has to do something immediately with it, sending down more photons is not going to help if the energy of the photon isn't sufficient to begin with. Ryan, make sense? Matthew, we good? Ada? Questions? Abby, okay? All right, in 15, you had to determine if the Planck's constant was given to you, what's the energy of the photon associated with a wave having a wavelength of 500 nanometers? So, real quickly, let's see that we can knock this one off. So we wanted to find the energy of the photon.
You skipped one.
You skipped 14.
Oh, shoot, I was so eager to get the problem. Okay, fine. What was significant about Einstein's explanation of the photoelectric effect? Real quickly, by being able to explain the physical phenomena that stumped classical theory, it lent great credibility to quantum theory, and it's why it was accepted. Okay? Remember, you know the deal. You've heard this before. When do we accept a new theory? When it does everything the old theory could do, but does something the old theory could not do. Okay? This new theory of light, this quantum theory, the fact that it could explain a physical phenomena that classical theory could not explain, specifically the photoelectric effect, lent great credibility to it, and that's why it was accepted. They want you to find the energy of the photon. Easy. All you need is the frequency, but they didn't give you the frequency. So how can we with the frequency? Well, C equals lambda times nu will give us a way of getting the frequency. All you have to know is the wavelength. Did they give us a wavelength? They did this time. Of course, I could give you 1 over lambda is equal to 10, 9, 6, 7, 8 times 1 over n sub 1 squared minus 1 over n sub 2 squared. So I could ask you, what is the energy of the photon associated with the second line of the Lyman series? So then you have to get the wavelength. Once you get the wavelength, then you have to get the frequency. Once you get the frequency, then you got to get the energy of the photon. And then let's turn it into matter
Yeah.
and see how much matter we can get.
That's my type.
Would you do that on the test, Mrs. Swan? Yeah, that's easy. That's easy. That's not hard. You guys should be able to do that. As it so happens, in this particular problem, I didn't make you go through and solve the Rydberg equation again because I gave you the wavelength, so you could start right here. And they weren't asking for the mass that we could produce by converting it into matter, so we're not going to be using equals squared. That means we're just using these two formulas. Now, to use this again, this is 3 times 10 to the 8th. This is meters per second. So that means our wavelength also has to be in meters again. So we need to take the 500 nanometers, and we have to change that. 10 to the 9th nanometers to 1 meter. That means I'm dealing with 5 times 10 to the negative 7th meters. That's what I want to put up over here. 5 times 10 to the negative 7th. And then I'll solve for frequency. When I do that, frequency turns out to be, what do you get, Matthew?
6.00 times 10 to the 16th.
16th what, Hunter?
Hertz.
Hertz, or seconds to the minus 1, that's right. Questions? Yep,
I got to the 14th.
that sounds actually better. That sounds more reasonable from what I recollect, based on the nanometer range. Did you do this step right here?
Yeah.
Okay, and you got 10 to the negative 7th?
No.
What did you get for your wavelength?
Oh, I converted the speed of light into nanometers.
Oh my God. Okay. I mean, you could do that. What'd you get as the speed of light in nanometers per second?
3 times 10 to the 17th.
Yeah, that's right. So you did 3 times 10 to the 17th is equal to 5 times 10 to the 500 rather times nu.
Yeah.
And so when you did this, how did you solve for your frequency?
I just divided it by 500.
Okay, and then you got to the 6 times 10 to the 14th, I mean, to the 15th? 16th, what'd you get?
Yeah, 16.
Can you see how 3 times 10 to the 17, and this is 5 times 10 to the 2, can you see how already that doesn't make sense?
Yeah.
Okay, so you use your calculator to do this, or you did it in your head?
Calculator.
Okay, sometimes that happens. You hit the wrong button. That's why you show your work. Okay, so this is a classic example. Why you want to show me your work. Show the value, the formula, plug in the values, give the final solution with the units, because you might hit the wrong button, like Matthew did, and I dock you a point for hitting the wrong button. As long as the math is there, I'm okay with that. Once you have the frequency, then we can go ahead and plug it in here. So E is equal to 6.63 times 10 to the negative 34th. Again, I'll give you Planck's constant on the test. You don't have to have that memorized. This is 6 times 10 to the 14th. When we solve, Carrie, what do you wind up with?
3.978 times 10 to the negative 19 joules.
10 to the negative what?
19th.
19th joules?
Yeah.
Okay. You want to put it in 3 or 4 sig figs is your final answer. Questions? Abby? You sure?
Yeah.
Yeah.
I just keep on like not understanding that I need to do more than what I'm doing. Like I thought that it was frequency in this one, and then for like for one of the other ones I didn't change it to meters. So
And I'm all about I'm all over that type of stuff. That's how you lose bunches of points.
Yeah.
Okay, so that's why we're going through this now, to make sure that you know what you're doing. Question?